up in the frozen
tundra.
Icelandic tundra.
I think I have beard in my mouth.
That happens. That happens. Yeah.
Here we are. We're just hanging with the bears. The polar bears.
The polar. Yeah, because we're going to talk about polar molecules with our polar bears.
Yes. All right.
Okay, let's get started.
Let's do it.
Okay, so we're going to talk about something called polar versus non-polar molecules.
Okay.
It's really important. It kind of have like a lot of properties, states of matter, and all these other things that we'll get to.
Oh, okay.
But it's all pretty much based because polar molecules do not share electrons equally.
Oh, okay.
So the electrons are in this cloud around the molecule. Polar ones are where the electrons kind of clump up around one atom because it hogs the electrons, if you will.
So kind of like a child with a really cool toy.
Yeah, exactly.
Doesn't want to share it.
Like when Mr. Koff gets his new toys, does not share them with us.
Got it. Right.
So what that does is the atom that hogs the electrons becomes a little negative because it's got more
electrons, because electrons are negative.
Exactly.
Okay.
And the other atoms are slightly positive, and positive, negative attract, causes all kinds of fun stuff.
All right. Okay.
All right. So an example of this is water. So those funny little like SE looking thingies, those are lowercase deltas.
Okay.
So they're lowercase deltas, which just shows partial charges. So
okay.
Delta with the plus sign is partially positive. Delta with the negative sign is partially negative.
Oh, okay. I get you. I get you. All right.
That's all.
Now, does the negative normally sit on the typical anion?
It would sit on the typical anion.
Okay.
Yeah, that's very.
I don't know if I'm using these correctly.
These air quotes, I don't know.
That's a Friends episode.
Oh.
I'll have to show it to you later.
I don't get friends in Iceland. So the stronger the atom is, the more electronegative it is. So the stronger it's going to pull those electrons in is the more electronegative ones.
Oh, okay.
So that's how we measure strength.
Okay, and how do I know which atom's more electronegative?
You'll just look it up on the periodic table.
Okay, got it.
Those values are given to you.
Got it. All right.
Yeah. So, all right. So the more electronegative atom will be the slightly negative one.
Okay.
The other ones will be the slightly positive one.
That makes sense.
You just look it up on the periodic table.
All right.
All right. Not too bad at all. So there's our friend water.
So in this case, the oxygen would be have the higher electronegativity.
Yeah, if you were to look it up on the periodic table, oxygen would be 3.5 with electronegativity.
Okay.
And hydrogen would be 0.9, so 3.5 is bigger.
So it's going to get the slightly negative. Okay.
Yeah, okay. Now, if the difference in electronegativity is less than 0.4, we call it nonpolar. It's not polar at all. We consider it an equal sharing or pretty close to equal. And so it has nonpolar properties.
Okay.
Between 0.4 and 1.7 in electronegativity difference, it's polar.
Okay.
And if it's greater than 1.7, those are just straight up ionic.
Straight up, here's my electrons. Thank you. See.
Yeah. Boom. Peace out. Okay. Microphone drop.
Got it.
Yeah.
Okay.
Now, here's where it gets a little bit weird here. Now, we can have polar bonds in a molecule, but if the molecule is symmetrical, the charges will kind of, the charge difference will kind of cancel out, and it'll still not act very polar.
Oh, okay.
So, we've been talking about, so here's an example.
Okay.
BF3.
Okay.
So we have, the F's around it. They're more electronegative, so they're partially negative and all that. It's symmetrical, though.
So
not polar.
Not polar. Okay.
No. H2O.
Polar.
Yeah, because we've used it as like the example of polar.
Okay. So basically, we're looking at that central atom, and if it has no unshared pairs, we would consider it symmetrical.
Yeah, pretty much.
Okay.
Pretty much. If we have lone pairs, it's pretty much not symmetrical.
Okay.
With very few exceptions.
All right.
All right, so we've been talking about these properties of polar and nonpolar and all that stuff. So let's just actually kind of maybe like go through what they are.
Okay.
So we have polar covalent and nonpolar covalent. So we're polar and nonpolar.
Got it.
So polar stuff dissolves ionic substances. So
like salt and water.
Salt and water. Great example.
Water being polar, salt being ionic. You put salt, water, mix it around, and poof, gone.
Poof, gone. Yes. Nonpolar does not dissolve ionic substances. See how they're different?
I do.
That's going to be a trend. Watch. Hey, polar has high surface tension.
So is that why those little bugs can walk on water?
Exactly.
Okay.
Yeah. Or like if you can put water and it'll kind of like bead up.
Make a bubble?
Yeah. Okay. Guess what? Nonpolar.
Can't.
It has low surface tension. Yep. Boy.
That's why when you use like acetone or like rubbing alcohol.
I thought you were going to say when you put a bug on oil.
Oh.
Go straight there. I don't know where you're going with that.
Yeah,
All right. Polar covalent are usually liquids or solids.
Okay.
So things like water.
Oh,
you
very
know,
good. Oh.
might shock you. Yeah.
Yep.
Non-polar, they're
Yes.
gases.
So like NH3.
NH.
No, that would be a liquid.
Yeah.
I
Like
apologize.
CO2.
Thank you.
And then last but not least, polar have high boiling points. Like water has a pretty high boiling
Yeah, it
point.
takes a while to get it to go.
Non-polar has a pretty low boiling point.
Gotcha. Okay.
Yeah. All right, and so here are some examples to help you practice. So here's what you need to do. You need to, first off, draw these Lewis structures.
Okay.
And before you do anything else, just see if they're symmetrical. If there's no lone pairs on the central atom, they're probably going to be symmetrical.
Okay.
Yeah.
So, for an H3, I would draw N,
Yep.
2 dots at the top, a dot, dot, and a dot around, and I would connect 3 hydrogens to that single dot.
Yeah.
And then I would notice that nitrogen has 1 lone pair.
It does.
So that would make it polar.
It would be polar. It's asymmetrical, so it would be polar.
Got it. Okay, very good.
Right?
Very good.
And you would do the same thing for CH4. All right? So
Okay.
you draw the Lewis structure for CH4.
Okay.
If it's symmetrical,
Yes.
if everything's coming off on the same directions and it's all symmetrical, then
Okay.
we know it's non-polar.
Got it.
And same for
Kind
CH4.
of like a haircut. Like it matches on both
you
sides.
want both sides to be the same
Right.
way haircut, right?
However, the neutron is not to match. I don't get
Yeah,
that.
I don't get it. It's
But I
weird.
live in the Ice Age in the Vikings where everything is even, as you can see.
Yeah, where we don't. Yeah.
And we don't shave very often.
No, it keeps the neck warm. Alrighty, so that was it. We're gonna try and stay warm, and we will see you all back in class. Bye.
See ya.